Hallmark Hotline, what is your emergency?
Hello, welcome back from Thanksgiving break.
Yeah, welcome back. Can you believe it's already December? I really cannot. It's so crazy that the year is almost over.
This is the Homework Hotline. I'm Becca. I teach math at Emily Griffith High School.
And I'm Nathan, and I also teach math at Emily Griffith High School.
And I'm Sam. I'm a science teacher at the Contemporary Learning Academy.
So do you wish you had access to a teacher to help you with math or science questions? Well, you actually do. Nathan and I are math geeks. We love to do math, and we love to help students. So call us with your math questions.
And I'm a self-proclaimed science nerd. I love to help students with science questions, so call those in if you have them.
We're here every Tuesday and Wednesday from 4:30 to 5:30 p.m. So give us a call at 720-424-1666. Because when you call in, we can help you a little bit more thoroughly on your questions.
You can watch our show in several different ways. For live broadcasts, you can watch us on Comcast, Channel 22, or you can go to livestream.com and search for EG Homework Hotline. If you would like to see some of our past shows, watch us on YouTube by searching for DPS TV Homework Hotline.
The Homework Hotline is sponsored by Contemporary Learning Academy and Emily Griffith High School. One of our Emily Griffith students, Lily, is also part of our team. Lily, why don't you tell the audience a little bit about yourself and what you do here?
Hi guys, I'm Lily and I'm a senior at Emily Griffith High School. The Homework Hotline loves to be accommodating to those of you who like to turn in your questions on social media, and I help get those questions over to our teachers. Also, I am the trivia queen, and I will give you guys a question at the top of each show, and before the end of the show, I want to hear the answer from you guys. The trivia question can be on any subject, but today is a history question. So call in with the correct answer and you'll win a prize. So today's trivia question is, what year was the first holiday law enacted by Congress in the U.S.? We will answer that at the end of the show.
Oh, interesting. All right, well, if you have an answer or think you might have an answer to the trivia question, you can give us a call at that phone number that Nathan gave earlier. It's on the top right of your screen, 720-424-1666. But for your information, you can also get in contact with us in some other ways. So again, if you have an answer to the trivia question, or if you've got homework questions, you can get a hold of us in the ways you see on your screen right now. The phone number we gave earlier, but you could also get a hold of us via social media at EG Homework on Facebook and Twitter. You could also text us 970-680-3771, or you can email us at homework@emilygriffith.edu. So a lot of different ways you can get in contact with us. Take your choice, but we will answer your homework questions, and you can also get a prize for trivia by contacting us in any of the ways you see on your screen. So speaking of social media, Lily is at our social media board, and she is going to give us our first question to answer for today.
So today's question asks, how do you find the area of an octagon whose sides are 9 inches in length?
All right, I can take that geometry question. So if you look at my screen, if you're watching, I went ahead and put up a picture of an octagon because it's hard for me to draw them. So when we find the area, so I'm going to go ahead and label what we know. We know all the sides are 9 inches in length, meaning every single side. I'm not going to write them all, but they're all 9 inches in length. So when you look at this figure, it's a little confusing at first, but if you think about it, you can actually draw diagonals through this, and what you actually have is basically a lot of triangles that you're looking for the area of. They should all be pretty much the same. Well, they should be exactly the same. So all I'm doing right now is trying to draw these out so you can kind of see really what we're doing here. So
yeah, anytime you have a shape that is irregular, that's not like a rectangle or a triangle, it's one of the good strategies is to break it up into shapes that are a little bit easier to find the area of, like triangles or rectangles.
Right, that you're just a little bit more familiar with.
Yeah.
So what we have here is basically I have 8 triangles. So if I can find the area of one of them, then I can find the area of everything. So what I'm going to do is actually we need to figure out the height first of all, because remember the area of a triangle triangle is going to be 1/2 the base times the height. So let's see. Got a right triangle here, and I've got a side of 4.5 because the entire thing is 9. So half of it's going to be 4.5. Right, 4.5 here and here. So this actually might be a little bit more work than I was thinking.
Is it a regular octagon, did they say?
They
Yeah.
didn't,
So
but I'm
that-
assuming, yeah.
Would that mean that your all the triangles, they're 60 or sorry, they're
45 degrees?
Yeah, exactly.
Yeah, so that's what I was thinking. Each one of these is 45 degrees. So this is 45. Then this is going to be 22.5, right?
So what I was asking is, would those be equilateral triangles?
They would they be equilateral? It didn't say it was a regular octagon. Right? So not necessarily.
Not necessarily, okay.
Right. So, I mean, there are a couple ways to do this. This might actually be kind of some trigonometry. So, if you know your trig ratios, I know I'm going to just draw one of these triangles out because I have right triangles. Shouldn't do it this way. So, I'm going to draw my right triangle. And I've got this is 4.5. This angle is 22.5 degrees. So what I actually really need is this value right here, right? Because that's going to be the height of my triangle. So I could think of this in terms of trigonometry and say that it's going to be tangent of 22.5 degrees equals my opposite over my adjacent. Right? So this actually becomes partially a trig problem. It might be an easier way to do this. It's just the way I'm thinking of it on top of my head. So what I would do is, what I like to do with these is think of this as like a cross multiplication problem. So I'm going to put this over 1. I'm going to multiply, and I'm going to get 4.5 equals x times tangent of 22.5. And I'm still solving for that height. So I'm going to divide each side by tangent of 22.5 divided by tangent 22.5. And I get x equals 10.86 approximately. And I'm going to do one of these because this means approximate. So this is the height. I know the base. So again, I'm going to try to figure out the area of one triangle is going to be half the base of 4.5 times the height of approximately 10.86. And Becca did this on a calculator for me, and you get 24.44 inches squared. And remember, this is just the area of one triangle. Where'd it go? Oh, you know what? Did you do 4.5 or did you do 9?
I did 4.5.
Okay, it should be 9.
Why? Oh, yes.
The base of the triangle. So I
see,
made a mistake
I
there,
see.
but you can just double that.
So we'll do,
So 24.44 times 2.
whoops, go to 48.887.
All right. So remember, this is just, we'll put 887. This is just the area of one triangle, but we have 8 of them because we have an octagon. There are 8 sides. So we will multiply this by 8, and that will give us the area of the entire octagon of 391.10 inches squared. So a little bit more work than I thought it was going to be off the top of my head. Just trying to find the area of that one triangle. But again, like Becca mentioned, it's really helpful to just break this down into smaller figures that you're more familiar with finding the area of, and then thinking about how many of those there are in there.
And the difficulty of the problem ranges depending on what you're given, what information you're given.
Right.
That had a very difficult piece of information to find in it that required the trig ratios.
Right.
Not necessarily finding area of octagons always requires trigonometry. Not
Right.
necessarily, it's just the pieces that we needed in that particular problem.
Like
Right.
Even given the diameter of the octagon, for example,
Right.
that would have helped
That would
you.
have been really
Right.
helpful.
Then you
yeah.
could have. Then it would have been almost a pure geometry
Right.
problem.
Exactly.
Looking at right triangles.
Or like Becca mentioned, if I knew it was a regular octagon, then I could have used that information to kind of shorten the
Is there a
process bit.
formula for a regular octagon area, or do you still have to break it up?
There is actually a formula.
Is there
for that.
really?
Yeah, but again, you have to be given
Sure that- yeah.
that centerpiece, so
Right.
you really need a little bit more information. Otherwise, it's kind of messy.
Well, nice job. That was like 2 math classes in one right there.
It was.
There you go. All right, well, let's switch gears and get another question from Lily.
So this one asks, substances that don't conduct heat are known as what?
Okay, yeah, sure. So the direct answer to that question is that substances that do not conduct heat are known as heat resistant or insulators. I think depending on the situation that you're in, you would either call something heat resistant if you were talking about its inability to pass heat through it, or you would talk about something as being an insulator if it was more about keeping heat inside of an area. Nate and Becca, can you think of a substance that you know that is really good at conducting heat?
Oh, conducting heat?
Like if you get something hot next to it.
Aluminum.
Yeah, right? Like can you imagine having an aluminum cup and having hot tea poured in it and then just trying to put your hands right on that cup?
Oh, that wouldn't be good.
Right, right. So what would you want your cup to be made out of?
Styrofoam.
Styrofoam would work
Styrofoam.
great.
Not really environmentally
Right,
friendly.
right. Pick something more environmentally friendly. Come on, Becca.
Ceramic?
Yeah, ceramic, right? Ceramic would be great. Even glass is better than any kind of metal. And what it really is it's all about how well the substance allows electrons to travel through. Because the electrons, the movement of the electrons in the atoms of whatever the material is, like a copper mug, for example, a copper mug will conduct heat really, really well because the electron path between the atoms of copper in that mug is very clear. It's very easy for those electrons to travel and knock into other electrons and thus transfer heat. And really the whole thing about heat transfer is it is all about electrons being able to knock into each other and how well they're able to do that, how clear their path is in a given substance will determine how conductive that substance is. Very conductive substances are things like metal, non-conductive substances are things like wood, ceramic, and glass would be somewhere kind of in the middle there. Does that make sense to you guys?
Oh, yeah.
Cool.
Yeah, and that's something you can really, I don't know, the real world, just match
That's
something you
real
know
world.
in the real world
Absolutely.
about that. You know.
I think it's always good in science if you can think about an analog from your own life
Right.
that somehow applies
Some
to the thing
example.
you're trying to. It can be hard when you're thinking about atoms sometimes, but there's usually always some kind of a connection.
Right.
So true. So true.
So true.
Well, guys, if you missed before, there's a phone number on the top of your screen, and the reason we have that there is so that you can call us and ask us questions that you're stumped on your homework about. And our specialties are math and science. We're not limited to math and science, but those are our specialties.
Probably take an English question if we had to. Maybe.
Yeah, I guess we'll try.
Yeah.
But the phone number's on the top of the screen if you missed it earlier. So let's go back to Lily again and get another social media question answered.
So he needs help adding together these complex numbers, and it asks in parentheses 3 plus 4i and parentheses plus 8 minus 11i in parentheses.
Okay, 3 plus 4i plus 8 minus 11i. Okay. If you cut to my screen, I'll show you what the question was. Now, they mentioned something about complex numbers. It said that in the question, so I'm going to explain that a little bit better. Complex numbers are made up of what is called an imaginary number and a real number. And that might sound crazy if you have never worked with imaginary numbers yet or ever heard of them. It really does. A lot of times students, when you say, we're going to learn about imaginary numbers, and they're like, what do you mean they're imaginary numbers? Fake numbers? What? But what imaginary number is actually, it deals with this concept of a negative square root. So a square root, let's say, for example, square root of 25. A square root, what it means is what do you square to get the number that's under that? So for 25, we could have an answer of either 5, or you can even have, and a lot of people forget, an answer of a negative 5, because negative 5 times negative 5 is 25, and positive 5 times positive 5 is 25. Now, when you get this idea of negative numbers underneath the square root, we can't do that because I couldn't say a negative number times a negative number is a negative number. That's not true. It's a positive. Or a positive times a positive is a negative. So nothing is going to make that true. So in order to deal with that, we have what is called an imaginary number, or I. So I, when you see that, is actually not a variable. It is actually some quantity, but it's an imaginary number. And that imaginary number is the square root of -1. And so that's what I is. And then a complex number is when you combine a real number and an imaginary number together. So for example, if I had something like 3 plus 2i, 3, that's the real part, and then 2i, that's the imaginary part, and together, that's called a complex number. So back to after that little kind of background chat about complex numbers, this person asked, how do we add these two complex numbers together? Fortunately, I, even though it's not a variable, it works very similarly to a variable, meaning imaginary numbers are like terms with each other. So, for example, if I had 3i and 7i, those are like terms, so you can put them together. So when we're adding them together, what we'll do, and I'm going to find my highlighter here, the like terms in this scenario, we've got 3 and 8. Those are real numbers, so we can combine those together. So 3 plus 8, that gives us 11. So that combines to give us our real number part of our answer. And then we can also combine like terms these imaginary numbers. So we have 4i and -11i. And putting those together, just like if it was 4x and -11x, be the same idea with imaginary numbers. We get -7i. So although imaginary numbers and complex numbers, the idea is kind of complicated, working with them and doing operations with them is not too bad. It works like other variables do, to be honest. But there you have it. And if you have any more questions about imaginary numbers or complex numbers, let me know, and I can give some more information about that.
That rings so true for me because I remember doing very well on a section of imaginary numbers when I took algebra, but coming out of it not really understanding what I'd just done.
Right.
But my grade was great. Because again, working with them is not actually that complicated.
It's not that complicated.
You learn the rules, you can do it, but imagining what that really means to have this imaginary number factor in, it just blew my mind.
It is a complex, not to be using the terms of it, but it is a complex idea. I mean, real numbers are tangible, like the number 3. I can have 3 things in front of you, and you can see what that is. And 3 plus 2, you can see what's happening with that. Right. Whereas imaginary numbers, they're not tangible, and so you can't, it's just a difficult concept to wrap your brain around because it's so abstract.
Definitely.
So, oh, I have a great imaginary number joke or comic that I show my students after they've learned about it. Lily can attest to it.
Yes, it's amazing.
But speaking of jokes, I heard you had some math jokes.
Yeah, I have so many math jokes. My students love them. They always tell me that I'm not very funny, and I'm like, try to be.
I don't know why they don't think they're hilarious, because I think they're hilarious too, but
whatever. It doesn't matter. As long as I think they're funny, that's what's really important.
That is what's important.
So let's hear it.
Do you know how you would write the expression of a thick crust pizza with height A and radius Z? What that would be?
I don't know. But I'm a science
Something
teacher.
with pie. Something with pie.
It would have pie. So it's actually pizza. So I can work out how that actually works out mathematically.
I get it.
If you go to my screen, I'll show
right.
you, and then obviously I will draw an awesome looking pizza.
Of course.
So if you think about a thick crust pizza, well, all pizza has some thickness, right? So it kind of keeps that cylinder shape. Like this is my pizza now. If you've ever been to Chicago, have you ever had deep dish pizza in Chicago?
Yeah, I have.
So they look a lot like this.
Indeed they do.
Right? And then they have some toppings, maybe like pepperoni, maybe anchovies, right? There you go, that's my pizza.
Beautiful.
Right, so really it's a cylinder shape. And we're saying I want to write an expression. It's got a height of A, so we go something like this, that's my height, and a radius of Z. So we talked about, I think, a couple times the the formula for the area. It's pretty good, right? It's like a solid
It's
looking-
Starting to
I
see
would,
it, right?
I would order this pizza.
It's beautiful.
So if really, again, we have a cylinder, so what we're doing is we're trying to find the area of like either the top or the bottom of the pizza, and then also factoring in that it's got some thickness in it. So we would say area equals pi r squared, which is just this area of each of these circles. But we also have to factor in the height because it has some depth to it, so times h. So if we said, and this is actually confusing that I'm writing area, so I'm going to do area here.
Oh, nice.
So what we're doing is, actually we're doing volume, not area, sorry.
I was just gonna.
Yeah.
You
Volume.
read my
There we
mind.
go.
Nicely done.
So volume equals pi, and then my radius squared, we said the radius is z, so z squared, and then times my height, which is a. So we could actually rewrite this and say the volume equals pi, pi. That's another way to write it. And what's another way we can write z
You
squared?
could say z times z, couldn't you?
Z times z. And then we got our a. So
Hee-hee.
That is
volume
really
of the
cute.
crust pizza is pizza.
That's a good one.
Brilliant. My kids don't appreciate it that much. You know,
Oh, they're a tough
I
audience
try.
sometimes.
Yeah, they are.
They are. Oh, I got one. I put it up on the screen. So if you want to check the screen now, I used this one before
Oh.
before all of the current.
Controversy.
Yeah, but let's just forget about all of that.
Put it off to the side.
Oh my god. was
And I
too
put this.
good.
I like to put this on my warm up before or right after my students learn about how to simplify trig stuff. So the reason, and we're laughing about this, but the reason this is funny is because so when you take the sine, hang on, I'll actually do the math here. So the sine of b divided by the tangent of b. Well, the tangent of b is the same thing as sine over cosine. So what we're doing is sine of b over 1 divided by sine of b over cosine of b. And then when you do division, you do keep it, change it, flip it. So, getting ahead of myself. Sine of b over 1 times cosine of b over sine of b, and then these cancel, and we end up getting cosine of b over 1, or just cosine of b cos b.
Brilliant.
So I use that one sometimes too.
Yeah.
You should have showed that to our class. That was like amazing. I almost cried just looking at that. Oh my god.
It's a really good joke.
It's kind of funnier
So
now
funny.
than all of that.
Oh
but
my
Yeah.
god.
That's my
That's
favorite
really
one.
good.
So that's my favorite math joke.
Oh goodness.
Do you
Oh.
guys have any others?
You know, now that you mentioned trigonometry, this is like a really quick one, and it's also really good.
Nice. Excellent.
If you go on my screen, have you seen
Oh,
this?
I like that one too.
Yeah, sine of Dreen divided by cosine of Dreen equals
Sine divided by cosine, tangent.
tangerine. Tan of Dreen.
Hilarious.
Yeah, so
I like it.
good trig
Clever.
jokes.
I like
I
it.
feel like
keep it low.
especially with the Cosby one, you could almost, if you could
Yeah.
just remember that, that would actually, you could help you in class.
It works
too,
out,
right? Yeah. That's really good.
It really does crack me up every time. All right. Well, I think I need a little bit of a break
Yeah.
to calm down for a minute. So we're going to take a break and look at a message from some of our sponsors.
Welcome to Nerd Necessities Network. You're probably thinking, what is Nerd Necessities Network? That's a good question. Nerd Necessities Network is a premier DPS TV show all about nerdy people, places, and things. You can check us out on Facebook and YouTube and all the social networks. That's a wrap!
Welcome back. That was nice little short break, enough for me to
Calm down.
down a little
That was
bit.
probably the nerdiest 3 minutes of my life.
Yeah. You could tell how much of math nerds we are with all of that, but
It was good.
anyways. We have a caller. We have a caller.
Yeah.
Caller, are you there? Hello.
Hello.
Hi,
Hello.
how are you?
I'm okay. How are you?
Oh. Can we make something better for you? Can we help you out a little bit?
Well, yeah, my teacher and I got in a little tiff today, so
Uh-oh.
I'm calling to settle the score.
Sure.
All
Get
right.
Let's
the
hear it.
right answer, the correct information, if you will.
Okay. All right.
Why is it warm in the summer but cold in the winter?
Oh, I'm gonna let you.
Sure.
answer that.
Sure. And can I ask, was the discussion, was the argument you had with your teacher, the tiff, was it about the idea that were you thinking that maybe the sun was closer?
Yeah,
In the summer?
basically, I told my teacher, I was like, listen, the Earth is closer to the sun in the summer. And my teacher was like, you listen, you're wrong, buddy.
Oh, that sounds like kind of an intense teacher. But he didn't help you out with the right answer. So let me see if I can help you here, okay? It is actually, your teacher is right. It is not because the sun is closer in the summer that it's warmer. In fact, the sun is actually just slightly closer during our winter to the sun. The Earth, excuse me, is. So it has actually much more to do with the tilt of the Earth. So can you imagine the Earth floating in space? Caller? Oh, might have lost the
Uh-oh.
caller,
We
but I'll
lost
just
our
I'll just
caller.
continue to explain it. Hopefully you're out there
Caller,
somewhere.
listen to the TV.
Hopefully you're out there somewhere
I'm
listening to
here.
this.
I'm sorry, my mom. I had to put you on mute. My mom was telling me dinner's ready, but I said I need to prove Miss Jameson wrong.
Well, I'm glad you got an extra minute for this. So, caller, can you imagine the Earth floating in space?
I can. It is right now.
Okay, yeah, perfect. So the Earth is not just floating straight up and down. It's actually floating at an angle. It's actually tilted. Have you ever heard that before?
Yeah, like on the axis.
Yeah, exactly. Earth's axis is tilted. So if you were like to stick a straw, let's say, right through the center of the globe, you would tilt that straw a little bit. And the Earth is rotating, as we know, right? That's what creates day and night. And it's also orbiting the sun. And that tilt is staying in the same direction as it orbits around the sun. So and what we really want to think about also, have you heard of the northern hemisphere and the southern hemisphere before?
Uh-huh.
Okay, cool. Well, so I've pulled up a picture on my computer here. So I don't know if you're watching the show right now and you're able to see the screen.
Yeah, you just pointed the camera.
Okay, fantastic. So yeah, so you can see I've got this fancy little diagram right here. You can see the sun there at the center of the Earth's orbit. Okay. And I'm going to point over here. Do you see where it says summer on the left side of the screen?
I do.
Okay, cool. Well, you can maybe see that at that point the Earth is tilted so that the top half of the Earth is closer to the sun than the bottom half of the Earth. Can you see that?
Okay.
So that is actually what's creating the summer in the northern hemisphere. Because the Earth is tilted toward the sun, the northern hemisphere is tilted toward the sun's rays are hitting the northern hemisphere directly.
Okay.
Whereas the southern hemisphere is tilted away, and so the rays that are hitting the sun, they're hitting it less directly and creating essentially less heat. Now, if you look at the other side of the diagram here, in the winter, are you able to see that the southern hemisphere is now tilted toward the sun?
Yeah.
And the northern hemisphere is tilted away, and so now the southern hemisphere is getting the direct rays of the sun, and the northern hemisphere is not. So in the northern hemisphere's winter, it's the southern hemisphere's summer, and vice versa. When it's the northern hemisphere's summer, it's the southern hemisphere's winter. Does that make a little bit of sense?
Yeah, so how isn't Earth swirling like the day in 24 hours? Won't the Earth, swirl around? So why isn't it more about, like, why isn't that side in an ice age? Or
Right.
how fast is it turning exactly?
Right,
That's
so
my question.
Definitely. So, and you probably know this, but the Earth is rotating around completely in 24 hours, right? So at noon, wherever you are, wherever you are on the Earth, you're getting the direct impact of the sun at that moment, right? And then over the course of the day, the Earth is turning away from the sun, the part of the Earth that you're on, and then turning back to it. So the Earth is rotating, but the tilt of the Earth is not changing. The tilt of the Earth is in the same direction, and that tilt stays the same as it moves around
Always?
the Earth. Well, so maybe if you're watching the screen, I don't know how helpful this is going to be, but my hand is the sun,
Okay.
okay? And then this pen is the Earth's tilt, okay?
Okay.
All right, and so the tilt is going to stay the same. Even as it moves around my hand, the tilt is still the same. So at this point, can you notice that the pen cap?
Forever and like forever?
Oh, not forever, ever, but for our lifetime. So it actually is true that the tilt of the Earth will change over the course of hundreds of thousands to millions of years,
Okay.
but not in a way that's going to impact your life or my life.
Okay.
Okay, but by the time, I mean, in our lifetimes, the winter and the summer will stay roughly in the same time frame.
Right.
Okay. Is that helpful?
Yeah, I mean, I got proved wrong, but I got the right answer finally.
Take that back to your teacher and show them that you know the correct answer.
Oh, I'm going to show her, all right. Thank you.
You're welcome. Take care.
Awesome. I think that also has to do with the length of the days too, right? So like when you're tilted, the southern hemisphere is tilted more away, you're getting less sunlight in one day.
Exactly.
You know, so that's why our days in the winter are shorter.
Exactly.
Less sunlight.
And you can model this really well by taking a flashlight and like
a globe.
A globe, or
Yeah.
even a
That's what my teacher
basketball.
taught me.
Right? Or a globe
Mm-hmm.
is perfect. Globe is excellent because then you can actually see the
Because
country.
you can see
right?
the rotating too.
Exactly. And it's that circle of light that the flashlight's going to create right on the globe that sort of shows you, okay, this is
Day.
where, that's where day is, anywhere where the circle of light is hitting. And you can go ahead and, you can rotate the globe around and see what day to night would be like. And then you can take that globe at the same tilt and move it around the flashlight to kind of get that sense of what summer versus winter would be like.
It's definitely interesting.
It is
So
I think
this
visually
Christmas,
that's
Australia is going to be spending their Christmas on the beach. Is that what you're trying to tell me?
Yes.
Pretty
yes.
much.
Absolutely.
How
Pretty
unfair!
Southern
That's why
Hemisphere.
plane tickets to Australia in the
that's
winter
true.
are
Yeah,
like
right?
$4,000.
Yeah, that's,
Go to
that's exactly
Sydney.
right.
Yep.
Everybody
That's
wants to
exactly
go in the
right.
winter.
Yep.
And if you travel in our summer down to South America, for example, you're going to end up arriving in their winter. You might
Yep.
be surprised to find them snow, you know?
Yep, that is true. Very true. Very interesting stuff.
It definitely.
Well, let's get some more questions answered. What do you have for us, Lily?
So I have a question that asks, two angles of a triangle measure 15 degrees and 85 degrees. What is the measure for the third angle?
All right, I can take that one. Another
Nice.
geometry question. So I'm going to go ahead and draw a triangle here. So we have two measures of a triangle are, let's make it look like this so it's more correct. 15 degrees and 85 degrees. So I've got an 85 degree angle here, and I've got a 15 degree angle inside of here. So you need to kind of remember some of the properties of a triangle, and that all triangles have, if you add up all the angles inside of a triangle, they're always going to add up to 180 degrees. So this really becomes like, when you know the properties of the triangle, it becomes an algebra problem. So I'm trying to find this missing angle. We can call it x degrees. So we know that all three angles have to add up to 180. So we can set this up algebraically and say 85 degrees plus 15 degrees plus this unknown x degrees has to add up to 180 degrees. So I'm going to combine my like terms. 100 degrees plus x degrees equals 180. And then we're just solving for x here, so we subtract the 100, and we end up with x equals 80 degrees. That would be that missing angle right here. And the reason why, if you think about like a triangle, if I had something like, let's say I had a 90 degree angle here, and I had a 30 degree angle over here. If this angle were not the right size, for example, if this was, let's make it really big, 100 degrees, it would go this way and I wouldn't make a triangle. So in order to make a triangle, they have to add up to that 180 degrees.
Oh, I wish we had that dynamic. What is that called? Geometer Sketchpad?
Oh, or GeoGebra, one of those where you can kind of
where
change
you
it.
can show, like, just adjust.
If you make one angle smaller, another angle has to be
Has to get
bigger to
bigger.
compensate, or you're not going
Yeah.
to get that triangle shape.
Kind of cool to see it as it moves.
Right.
Yeah.
Very neat.
Well, we are going to take another break. We're going to, well, check it out, actually. Commercial time.
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. Never mind from when, why, or how.
'Cause now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
Grilled special and an entree, order in. Open up.
If you're more of a hands-on learner and you just want to get thrown into the fire, and if you just want to get in there and just do it, this program has a lot more to offer.
So what we do is get in the classroom and we go over how to make certain items or methods on how to do certain things. And then we walk literally from the classroom over to the kitchen and we make the same product that we just spent 30, 40 minutes talking about. Once we make that product, then we bring it back into the classroom and we critique it and see what we could have done better and what we could have maybe worked on a little bit more.
So what I want you to do is go get 2 little black sodas.
My intentions are actually to see if I can go to some sort of culinary school in Italy. I love Italian style food, and my intentions after doing all this and all this schooling programming is starting my own Italian style restaurant.
They might want to work in a catering company for a while. They might want to work in a hotel or a restaurant, throughout their long career. And no matter what they end up doing, I know they're going to feel comfortable in that type of situation because they have a strong foundation to build upon. They'll feel comfortable no matter where they end up.
Hello. Hi. What are you waiting for? What are you afraid of? You jump right in. Shooting video. You have a camera in your hand more than a book. Learn from my dad. He won't waste your time. Learn video production. My dad would teach you. You can do this.
Hello, welcome back. Hopefully you enjoyed our commercials. They're wonderful. We have a Facebook discussion to talk about. So Lily, share our interesting thing on Facebook.
So today we're going to be talking about the science of snowflakes and all the fun facts about snowflakes that nobody knows. So yeah, basically that's what we're going to be talking about in a good summary. But I don't know who wants to start us off. Who has a better?
Well, I mean, with all of our snow we've been having, I mean, maybe it's been inspiring you thinking. A lot of people have heard about the fact that there's no 2 snowflakes that are the same. They're like fingerprints or whatever. Right. So we were curious, is that really true? Why is that? And so we posted an article on Facebook that talks about that, why no 2 snowflakes are alike.
Yeah, very cool. And I think snowflakes are very cool because we understand a lot about water and how it works and what it looks like when it freezes. But at the same time, there are still mysteries about snowflake formation. Mm-hmm. There are still things that we don't understand that even the best science has not been able to figure out. I've got a picture on my screen, if we could jump to that, of snowflakes and how they form at different temperatures. So you can see down here, along the x-axis, we have temperatures in Celsius and Fahrenheit, and then there's a very clear division of the types of crystals that we get depending on what the temperature is.
So I like that you say crystals, though. I mean, they're not white.
Right.
It's clear.
They are
like
clear crystals.
Yes.
Right, but their size and their shape is really efficient. This is true of most ice. Is really great at reflecting light, and all that reflection, when all colors of the light spectrum are reflected, we see that as white light. And so, and you can totally see this if you go and look very closely at snow. You can find clear crystals that you can see through. But when you take a step back and you look at a patch of snow or a large sheet of ice, it often has that white sheen because it's so good at reflecting light.
I kind of see it sometimes if you're outside and a piece of snow lands in your glove or something, and you're like, wow, it's like actually pretty beautiful the way it's constructed. So.
You've really got to get in there close to see some of the beauty of the crystal structure. And it's very interesting. So there's some specific temperatures that form different things. So at -2 degrees Celsius, thin plates and star shapes grow. At -5 degrees Celsius, you get columns and slender needles that grow. You get another set of plates and stars that are slightly different at -15 degrees Celsius. And you end up getting plates and columns, again, slightly different types of plates and columns at -30 degrees Celsius. And the other thing that can change the shape of a snowflake is the humidity of the area where the snow is falling. So snow crystals are going to look different on a humid day versus a very dry day. And minor changes in temperature and humidity can have a big impact on what kind of a crystal you actually end up with.
Do the shapes based on the temperature, does that have to do with like how fast it freezes?
You know, I actually can't say 100%, but I'm gonna go with yes, because I know that at least from geology, when we think about different crystal structures that form in rock, it has everything to do with the speed at which those crystals are able to take shape. So I'm imagining that that's another big factor, right? So if the temperature's dropping rapidly at the time, if it's holding steady, you're going to end up with different types of snowflakes, right?
Yeah, there's a lot of variables in there.
There's so many variables, and that's one of the reasons why, you know, you get all these different unique snowflake shapes.
Well, and it should be noted that this is all occurring in the clouds. This is not happening as it's starting to rain. It's not like, oh, it's raining. Oh, no, it's cold. The rain's going to turn to snow. When that happens, that is sleet, right? That's considered sleet. Yep. And then hail is just a piece of sleet that's collecting water and kind of like getting larger as it's getting to the ground. So they're all formed in different ways.
They definitely are. And hail actually is really interesting because oftentimes hail, we're talking about a piece of sleet, right? A freezing raindrop getting kicked back up into the sky, getting another layer of water put around it and falling down. And large pieces of hail, it's the updrafts and downdrafts, and large pieces of hail have tended to travel multiple times back up toward the clouds before gaining a mass that's enough to bring them down to the ground.
That's why you see a lot with tornadoes.
That is exactly right. That's exactly the case.
Makes a lot of sense. Weather is so interesting. It really is interesting.
It really is. It totally is. And you know, just to add a little bit to this, I mentioned that it was sort of a mystery still. There's a quote from a snowflake scientist out there, and he says, it's a mystery as to why snowflake shapes go from plates to columns as the temperature lowers. And that's one of the things I've been trying to understand. It's been a mystery for about 75 years, and it's still unsolved.
Right, I notice it does columns at certain temperatures, and it does the plates at certain temperatures.
Right.
But it kind of alternates between the two.
Yeah,
so the lowest temperature, it's the plates, and then it a little bit higher is the columns, and vice versa.
Yeah.
Interesting. Very, very interesting stuff.
That is. Interesting world,
so
for
check
sure.
out our article on Facebook. We always have interesting stuff on there, or at least we think it's interesting, us math and science nerds. So check it out if you are nerdy like us. We have a caller, so we're going to take that. So, hello, are you here? Can you hear us?
Yeah, I can hear you guys.
Hi, how are you?
Good. How was your Thanksgiving break?
It was awesome. How was yours?
Really great.
It was good. I was in Vegas.
Ooh, that's fun.
Great place for Thanksgiving.
Fun. Yeah. All right. What happens in Vegas stays in Vegas.
Hopefully you have something to be thankful for after.
Yeah.
Except for the homework. Homework's still in Vegas.
True. So is that homework giving you some trouble?
Yeah. It's kind of with my truck too.
Okay, how can we help you?
Yeah, so my truck is traveling 75 miles per hour. How many meters does my truck travel in 1 minute?
Do you mean kilometers per hour?
Yeah, kilometers per hour.
Okay, because that would be a tougher conversion with miles to meters.
Right,
You
you have
said-
to know English to metric.
Yeah,
So-
exactly.
Tell me one more time. You said your truck is traveling at 75 kilometers per hour. And then what did you need to find out?
How many meters does the car travel in 1 minute?
In 1 minute. Okay. So how many meters, and then per minute?
Yeah, kilometers.
So it's kilometers, but then we need to find how many meters per minute or kilometers per minute?
Meters per minute.
Meters per minute. Okay. So this is called unit analysis. And what we're really trying to do is trying to convert two different units. We're trying to convert these kilometers, and we're also trying to convert the hours to minutes. So we're converting a distance from kilometers to meters and then hours to minutes. So there are two conversion rates that we need to know. We need to know how many meters are in a kilometer. Do you know how many meters are in a kilometer?
No, I can't remember that.
Do you know, so the prefix of it actually gives us a little hint as to how many. Do you know what kilo, what that prefix means?
Kilometers, which is 1,000, right?
Uh-huh, exactly. So that kilo means 1,000. So that gives us a clue. It's telling us that there are 1,000 meters in 1 kilometer. So we need to know that conversion rate, so how we can convert meters to kilometers. And then also we need to know about how many hours to minutes. So do you know how many minutes are in an hour?
60.
Good, okay. So we have our two conversion rates that we need. We have 1,000 meters in 1 kilometer and 60 minutes in an hour. So what we do is we're gonna set up that 75 kilometers per 1 hour. We're gonna set it up as a ratio. And then what we're trying to do is we're trying to change or almost get rid of the kilometer units and replace them with meters. And then we're also trying to get rid of the hour units and replace them with minutes. So one way that we can get rid of a unit is by, how would you explain? It's by multiplying. If we have kilometers on our numerator, we also need them on the denominator, because if it's the same on the numerator and the denominator, we can cancel them. Does that make sense?
Yeah, that makes sense.
Okay, so what we're going to do is we're going to use this conversion rate, 1,000 meters per 1 kilometer, and I'm going to put the kilometers on the bottom. Oops, that's really ugly. I'm going to put that on the bottom because what will happen is they will cancel. So kilometers, cancel. And so I'm being very careful in the way I'm setting this up, and that's really how these problems kind of have to be done. So I have 1,000 meters per 1 kilometer. I use that conversion rate. Now what I've done by multiplying it by this ratio is I have eliminated kilometers. Now the reason why I'm allowed to multiply by this is that whole thing, it actually just equals 1. Because 1,000 meters and 1 kilometer are the same exact distance, right?
Right.
So something over itself just equals 1. And when I multiply something by 1, I'm not really changing it, I'm just changing what it looks like. Think of like equivalent fractions. Does that make sense so far?
Yeah, so you just do 75 times 1,000.
Exactly. And so what that's doing so far is that's changing our kilometers, because the kilometers are canceling. It's changing it into the meters that we need it in. So that's one piece that we have to do. The other piece we have to do is change our hours into minutes. So we're going to do the same thing, multiply, by, we're going to use our conversion rate, 1 hour and 60 minutes. But this time I'm going to put my hours on the top. And the reason, again, I'm going to put the hours on the top is just the same as the reason I put kilometers on the bottom before, is because I want my hours and hours, I want those to cancel. Now I've turned my kilometers to meters, and I've turned my minutes or hours to minutes. So what's going to happen is I'm going to multiply all my numerators together. So 75 times 1,000, like you said. And I get 75,000. And what is the unit for that? Do you know what
per squared?
So what unit is left on the top now? So I did my 75 times 1,000, and then what unit is left? Meters, kilometers? Yes, meters. That's what's left. So we have 75 meters. That's what we wanted. And then on the denominator, we're going to do the 1 times the 1 times the 60. So that gives us 60. And then what's our units left on the bottom, the denominator?
Minutes.
Minutes, exactly. Now, we now know that your truck's going 75,000 meters per 60 minutes, but you asked you wanted per 1 minute. So we're going to find a unit rate. And to find a unit rate, you do division. And so we're going to do that 75,000 divided by the 60 minutes. And we end up getting 1,250. And our units are going to be the same as before, which is meters per minute. So you're going 1,250 meters per minute. Does that make sense?
Yeah, that makes sense now.
Okay, awesome. Yeah, what this is called is unit analysis. You can use this anytime you're making any kind of conversion. It's a really great method and kind of an organized method too to solving problems like these. So is there anything else we can do to help you today?
No, that'll do it. Thank you.
Awesome. All right. Thanks for calling Homework Hotline.
I like the way that you broke that down. These kind of problems always remind me of why the metric system is better, and we should use it.
I know.
So much better.
I know. We don't have to look up those conversion rates.
Right.
We can use prefixes
Use
to
the
tell us.
prefixes,
If
so
it was
easy.
miles to feet, that would have
I
been
know.
A little
All
tougher.
So actually, we're going to take a second really quick and remind everybody what the trivia question was for today. In case you think you know the answer, you just have a guess, just go ahead and call in. The question was, what year was the first holiday law enacted by Congress in the U.S.? So again, if you think you know the answer to that, just give us a call, and the number is in the top right-hand corner of the screen.
Guesses are welcome. Guesses are welcome.
Yes, they are.
Right.
All right, so let's get another question answered from Lily.
This one asks, carbohydrates are made of which 3 elements?
All right. Okay, this is a relatively simple one here. I'll try to keep it simple and short. So carbohydrate, actually the clue to what is in carbohydrates is right in the name. So carbohydrates, hydrate, you might realize relates to hydration, relates to water, okay? So a carbohydrate is a molecule that has 1 carbon atom to every 2 hydrogen atoms and 1 oxygen atom. In other words, it's a carbon attached to an H2O. It's a carbon attached to a water. It's a carbohydrate. So the typical carbohydrate that we have is glucose, so that's the one we talk about very commonly, and the formula for that is C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens, but again at that comparative rate of 1 carbon per water molecule. So carbon, hydrogen, and oxygen is the answer to that question.
Nice.
Yeah, fairly straightforward.
I really like when words give you the answer.
I love that.
I
love that. You don't get that from other organic molecules in the same way. Carbohydrate is very easy. And it's cool too because it's like plants took carbon and they took water and they fused them together and that's sugar. It's kind of wild.
Pretty simple.
Yeah.
All right. Well, sadly, we didn't get a caller for our trivia question answer. But I still want to know the answer, so.
Yeah, come on.
Let's hear it, Lily.
So the trivia question again today was, what year was the first holiday law enacted by Congress in the U.S.? And that was 1870.
1870. So what exactly do we mean by the first holiday law?
I'm guessing it means
what's a holiday law? What exactly do we mean by that? Let's clarify.
A day off?
A day off.
That's
for
what I'm
all
thinking,
government
but I don't know. I'm
employees.
just guessing, yeah.
Oh, I like holiday laws.
Right.
Yeah,
right.
I have more of
appreciate
those.
them, yeah.
More holiday laws.
I wouldn't complain.
So, but before 1870 then, what happened? Did people just have to?
Yeah, government employees had it tough, I guess.
Yeah.
They just didn't get off work, I guess. I don't know.
I think labor laws were a lot different in the 1870s, so.
They probably were.
Yeah.
So what were the
non-existent.
first holiday laws?
So the first holiday law was the law passed in 1870, and
Which
it
holiday?
allowed for New Year's Day, Independence Day, Thanksgiving Day, and Christmas Day. Apparently also any day appointed or recommended by the President of the United States as a day of public fasting or feasting. I'm not sure. Partying, public partying, whatever it might be. But the President, it looked like, was able
Feasting,
to
not
declare another holiday if he wanted to.
So these are national holidays, like just U.S. And
Mhm.
a lot of people, we don't take the time to think, do they happen in other countries? Like,
Right.
does
Yeah, like-
that mean?
We just had Thanksgiving, but Thanksgiving traditionally is a very American holiday, right? It was developed here.
Right.
Canada has Thanksgiving, though.
But it celebrates a different thing, does it not?
It's actually, it's not the same time. I mean, it's celebrating giving thanks.
Sure.
It's not the same time we do it. It's the first Monday in October, and it is giving thanks for the harvest season is the purpose of it. So, but they do have Thanksgiving.
Yeah, I was reading, so in Australia and the Philippines, they also celebrate Thanksgiving. And for both of those countries, a lot of it had to do with like U.S. influence. So
that makes sense.
Australia, for example, Thanksgiving was brought by, I guess, American whalers. So like in Australia, they kind of brought the holiday and probably celebrated it.
Mhm.
And then maybe some Australians picked it up. But a lot of heavy American influence there, obviously.
Yeah.
Well, they aren't always the same, the same purpose. Grenada celebrates Thanksgiving, and it's around the same time as ours, but it doesn't mark the same thing. What it marks is the anniversary of the U.S.-led invasion of the island of Grenada in 1983. So not necessarily always the same.
Yeah, I'm sure different countries
Same
have
thing.
different reasons to give thanks. You know,
Mhm.
It's kind of a funny thing.
Yeah, that's very true.
Yeah, and in the Philippines, again, like the Philippines was a U.S. colony for a while, so they brought the tradition there, and I guess it was kind of gone for a while,
right,
and then came back again, but it was never revived after, I think it was 1986, they
That's so
stopped
interesting.
celebrating the holiday. But,
Well, I think everyone should have Thanksgiving because I love turkey and eating.
Yeah.
And
it's a great holiday.
Hanging out
Family
with family
too.
and
I do
friends.
too,
Yeah,
right.
But mainly the turkey. And
Yeah.
the eating, right?
I just think it's a good holiday.
It's a
I like
great
it.
one.
It's a really
It
good
really
one.
is.
So, what do you think, Lily?
I don't know. I like Thanksgiving. There's actually a lot of, I don't know if you guys heard about the National Mourning Day. Instead of Thanksgiving, it's where like Native Americans, instead of celebrating Thanksgiving, they celebrate National Mourning Day. But
Doesn't sound nearly as fun.
I think it's more appropriate for Columbus Day. I mean, I'm
I
Native
think you're right.
American and my family just likes to just eat together. I mean, that's really what we think Thanksgiving is about, is just being with your family, but I
Yeah.
think it was kind of interesting.
I know a guy who calls it Thanks-taking Day for similar reasons, because he's a little bit bitter about what it represents.
Right. Yeah.
But it's
Right.
a good time just to get together with people.
I agree with you. Just think of it as getting together, giving thanks.
Yeah, you don't always
Eating
have to look
food.
at the bad parts of
Right.
things. Like,
Did you all do any like big family Thanksgiving feasts or anything, or?
No, my family's not here.
Mine either.
Mine either, but I did a big friend family party
Friendsgiving.
up in the mountains.
Those are always fun.
It was really, really
Yeah.
great. We had a really, really good time.
We kind of did the same thing, and not to plug Popeyes, but I got a Popeyes turkey this year, and it was pretty awesome. Yes.
That's great. It's good to know.
That was
Cajun.
nice not to cook, though.
Yeah, all we had to do was thaw it out and then throw it in the oven for about an hour and a half.
I'm
really good.
thinking this is the way to go now.
Yeah, I'm thinking I wish they sold it all year, because I would definitely not just wait until
Popeyes
Thanksgiving.
turkey,
It's
that
pretty
does
nice.
actually kind of sound good. All right. Well, sadly, we're back from Thanksgiving break, and which means we have more homework.
All right.
It's just how it is.
That's how it goes.
So if you have homework questions, maybe you didn't get them answered today, you do still have tomorrow. We'll be back tomorrow, same time, 4:30 to 5:30 p.m. In the meantime, you can send your questions into social media, and Lily will sift through those and pick out some that are for us. But welcome back. Sorry that you got to work again, and we'll see you again tomorrow. Thanks.